When you type a website URL and press the Enter key, a complex web page appears on your screen almost instantly. That seamless user experience masks the execution of thousands of discrete operations occurring in the background. A modern web browser operates as a highly deterministic, real-time compiler, often written in low-level languages like C++ or Rust. Its primary function is to ingest raw alphanumeric text from a distant server and translate it into a complex, interactive graphical matrix on your local machine. To accomplish this, the browser executes a strict 13-step rendering pipeline, completing the entire process in a matter of milliseconds. Understanding the exact mechanics of this pipeline is the only way engineers can diagnose why highly capable devices still stall and stutter when loading seemingly simple web applications. The pipeline begins the moment the browser parses your URL to identify the protocol, like HTTPS, and the target domain. Because computers route traffic using IP addresses, the browser must first query the domain name system, or DNS. As we see in this network topology map, a request travels to a DNS directory, which then returns the specific numeric IP address of the target server back to the client. Next, the browser establishes a routing path using a TCP connection, followed by a TLS handshake to encrypt the data in transit. Through this secure tunnel, the client sends an HTTP request directly to the host server, asking for the web page data. The server responds by returning an initial payload. This consists entirely of a continuous stream of raw, unformatted HTML text. At this stage, the screen remains blank. This text is merely a structural blueprint, requiring the browser's engine to scan the data and execute its internal transformation pipeline to make it usable. The browser reads this incoming HTML document strictly from top to bottom using an internal HTML parser. This diagram illustrates the parser module in action. As it ingests the raw HTML string, it converts text tags into a memory representation of the page structure, generating a branching data architecture called the Document Object Model, or DOM. As the parser continues down the document, it inevitably encounters links to external CSS style files and immediately triggers their download. The browser parses these style sheets into a secondary parallel data structure known as the CSS Object Model, or CSSOM. While the DOM dictates structure, the CSSOM establishes the strict visual rules dictating how every element should eventually appear. Simultaneously, the browser must also download and execute JavaScript files using its dedicated JavaScript engine. Because scripts have the authority to manipulate both the DOM and the CSSOM dynamically, they introduce a structural dependency conflict. To prevent rendering errors, the JavaScript engine enforces a strict pause on the HTML parser. The DOM tree halts its growth entirely until the scripts are fully resolved. Because of this architectural dependency, JavaScript creates a massive performance bottleneck. The visual structure cannot finish compiling until the script execution is complete. Once parsing is complete, the browser enters a synthesis phase to combine the structural framework of the DOM with the styling rules of the CSSOM. The two distinct data structures overlap and merge into a single unified architecture called the render tree. The defining characteristic of the render tree is that it strictly contains elements that will actually be visible to the user. During this synthesis, the browser initiates a mathematical pruning process. Any nodes hidden by CSS rules, like a display none command, or hidden structural tags are severed and discarded from the tree entirely. Reducing the total volume of nodes at this stage is a crucial optimization step to preserve computational power later in the pipeline. The resulting render tree provides a definitive, optimized map of the user interface. It is the required input before the browser can generate physical pixels. With the render tree finalized, the browser enters step 11, the layout phase, which front-end engineers frequently call reflow. During layout, the engine calculates the exact geometry for every single node in the render tree. As seen in this visualization, abstract nodes map onto a rigid grid, snapping into distinct wireframe bounding boxes. These calculations depend entirely on the user's specific viewport dimensions and device constraints to lock in physical sizes and screen positions. Next comes step 12, the painting phase, where the calculated geometric layout is rasterized. Painting is the process of filling those empty wireframes with pixels, generating the text, background colors, borders, and shadows. However, the browser does not paint everything onto a single flat canvas. Instead, it draws different elements onto distinct, overlapping visual layers. This layered approach prepares the data for the final phase, step 13, compositing. The compositor takes all of these separate painted layers and stacks them together to produce the final two-dimensional image you see on your monitor. To execute this quickly, the browser offloads the compositing workload from the CPU directly to the graphics processing unit, or GPU. Separating the interface into distinct layers and relying on the GPU to composite them allows the browser to execute smooth scrolling and complex animations without forcing the system to recalculate and repaint the entire page every millisecond. The entire rendering pipeline operates as a strict sequence of dependencies, cascading from the initial network fetch all the way down to the final GPU composite. Delays early in the chain, like massive JavaScript payloads or unoptimized render-blocking CSS, can prevent the render tree from ever forming. But once the page is loaded, the single most computationally expensive performance penalty comes from continuous layout recalculations, or reflows. Looking at the complete pipeline flowchart, if a JavaScript function dynamically updates the physical geometry of an element after the initial load, the browser must discard the current layout phase. A reflow forces the rendering engine to rerun the layout, paint, and compositing stages completely from scratch, which devastates frame rates and causes visible stuttering. This contrasts sharply with a simple style update, like changing a background color. A color change only triggers a repaint, entirely skipping the heavy geometric math required by a reflow. Front-end performance is a direct result of managing state changes, so they do not force the browser engine to needlessly reconstruct its rendering pipeline.